The Biot-Savart Law gives us a starting point for calculating the magnetic field of moving charges. It was determined empirically to be this formula. That variable, B vector. B vector is the variable that we use to represent magnetic field. And that B vector is equal to mu naught, the permeability of free space. The permeability of free space is a constant, and it has an exact value given by 4 pi times 10 to the minus 7 Tesla meters per amps. Now, this constant describes how space itself responds to the presence of a magnetic field. Mu naught serves for magnetic fields much like epsilon naught, the permittivity of free space, serves for electric fields. Epsilon naught corresponds to our static charges generating electric fields. Mu naught corresponds to moving charges generating magnetic fields. Mu naught is multiplied to Q, and this is the value of the charge that is the source of the magnetic field. So this is our source charge. Now our source charge must be moving with a velocity in order for there to be a magnetic field. And this velocity, when we cross it with r hat, gives us the direction for the magnetic field at that point. This r hat is a unit vector indicating the direction of the position of the point at which we are evaluating the magnetic field relative to the position of the point charge. And r is the distance from our source charge to the point at which we are evaluating the magnetic field. So this right here is the Biot-Savart Law giving us the ability for calculating the magnetic field due to a moving charge. And the unit of magnetic field, we name it in honor of Nikola Tesla. The unit is the Tesla. And 1 Tesla is equivalent to 1 Newton per amp meter. Now, this is the version of the Biot-Savart Law using a cross product. But you might remember that the cross product of two vectors can be expressed in terms of a magnitude and a direction given by the right-hand rule. So it's often more convenient to write this version of the Biot-Savart Law in terms of the magnitudes instead of cross products. And what we have here, what's different is, notice we have v, the speed of the source charge, times the sine of the angle between the source charge's velocity and the relative position vector of the point at which we are evaluating the cross product. So let's illustrate this out with a sketch. So here is the Biot-Savart Law. The magnetic field is equal to mu naught over 4 pi times the value of the source charge times the cross product of the charge's velocity and the direction of the relative position vector to the point at which we are evaluating, divided by the distance squared. Now this can be expressed using what we know about cross products. Remember, the magnitude of the cross product between two vectors, A and B, is equal to the product of the magnitudes of those two vectors times the sine of the angle between them. And we will say the sine of the reference angle between them. So let's apply this to our positive charge. So here's our positive charge, and let's say our positive charge has a velocity that lies along this line. Let's say we want to evaluate the magnetic field due to that positive charge at this point right here. So here's the point of evaluation. Now, in order to evaluate that, we're going to need to know the relative position of that point to the location of our source charge. So we will indicate that with this vector right here. This vector is our vector, the relative position of the point at which we are evaluating to our source charge. Now there is an angle between our vector and the velocity vector, and that's this angle right here. And so we will say that that angle, we'll label it as VR for the reference angle between the line of velocity or the velocity vector and our relative position vector. Now the unit vector, of course, is a vector of magnitude 1 that is in the same direction as our position vector here. And so with this, we could express that the magnetic field is equal to mu naught over 4 pi q for the value of the source charge V cross R. Well, remember, V cross R is going to be can be given by the magnitude of the cross product between those two vectors. And the direction is going to be given by the right-hand rule. So I'll just say right-hand rule gives direction. Well, the magnitude of velocity and that relative position unit vector is given by the product of the magnitudes of each of those vectors times the sine of the reference angle between them over r squared. Now remember, the magnitude of a unit vector is exactly equal to 1. So we could say that this is mu naught over 4 pi q v sine of the reference angle between the velocity and the relative position vector, where remember, v is just corresponding to the magnitude of our velocity. And this expression gives us the magnitude of our magnetic field. Now for the direction is given by the right-hand rule. So if we were to place our thumb pointing along the line of velocity and curl our fingers around that line of velocity, remember, we would get the direction of the orientation, rather, of the magnetic field lines. So if we could extend our hand at that point in which we are evaluating the magnetic field, we would see that the magnetic field would point at a right angle. That's not quite down. It might look like it's at a diagonal, but this is something, if we could just draw a concentric circle for perspective, we would see that the magnetic field vector is tangent to the circle of the magnetic field line at the point at which we are evaluating, with the orientation given by our right hand. And once we use the right-hand rule, we could apply that to determine the direction of the magnetic field at that point.